Welcome back. So we finished the past hour with this Swiss cleanup that we call a minimal basis, right? So who would be able now, if I give you a set of functional dependencies that's very messy, who is able to clean it up on paper? Very good. So you see, it's again something mechanical. Just do it and do it and do it, and then, and the book is probably full of exercises to do that. If you want them, they give you functional dependencies and ask you to clean them up. Okay. Or you can also put to yourself random sets, just generate randomly and then solve them. Okay. So I summarize what we've done. So we've looked at functional dependencies, at super keys, at candidate keys, at primary keys, which is the one you pick from the candidate keys, prime attributes we've looked at the closure of a set of attributes, very mechanical. We've looked at the 5 actions. We've seen that 3 of them are actually Armstrong actions that you can use in order to transform sets of functional dependencies. We've seen that one particular way of transforming a set of functional dependencies is to clean it up, and that's what we call a minimal basis. But now it seems like this is just doing math for fun and not very useful, right? So why are we doing all that? And now we are going to start getting back to the tables that were interesting us and trying to go to best practices. So now we are slowly making our way back to the tables. And the first thing that I'm going to show you is what happens to the functional dependencies if you project a table. So you have here on the left a table that has 4 attributes and that has a few functional dependencies. A gives you C and A gives you B. Imagine now that I'm projecting that table to just A and B, right? So pi, you remember pi, right? Pi is the projection from the relational algebra, and so I'm projecting just to attributes A and B. And you agree, I get what you have on the right, right? It's A, B, E, F. That's just less columns, okay? Would you agree that what happens to the functional dependencies is that A gives B is preserved, but A gives C goes away? Who agrees with that? Okay. And you know the 2 reasons, right? A gives you C goes away because C is not here anymore anyway. So it doesn't even make sense anymore. And A gives you B, well, it's still true, right? If B was a function of A before the projection and you project, and it's still a function of A. That doesn't alter the functional dependency. I'm not saying the proof is trivial, but at least it's intuitive, right? Okay. So then here's a different set of functional dependencies, right? I'm just assuming now it's, of course, I'm not saying they apply to the table. The table is an example. When I put the functional dependencies in there, I have the table universe in mind, right, generally. So imagine that now I have the functional dependencies A gives me C, C gives me B, and A gives me B. What do you think I would have in the projection? I would like 2 of them. Anybody has a first? I did the easy one. There is one that is easy. Yes? No, actually, there's only one. Sorry. Yeah.
That A implies B.
Exactly. A gives you B. You see that the other ones, A gives you C and C gives you B, so C is not there. You could still combine them with the transitivity rule, but you still get the same one. So you basically get A gives you B. All right, so that's the projected set of dependencies. But can we generalize that? Because here we kind of waved our hands, you know, trying to find them and so on, but is there a more systematic way of doing that? And in fact, what we really need to do is, it's theoretical what I'm going to tell you because you don't do it on paper, but you basically try to derive all possible functional dependencies ever, the quintillion functional dependencies that would follow from S. So apply all the rules you can and derive them all. And then you only keep those that only involve attributes in the projection. Who agrees that this is sensible to do it this way, right? So what that means is, so the trap to not fall into is to only look at this and to just ask, okay, we don't keep, and we keep, right? This is wrong because here you're not using the fact that there might be derived dependencies that could be projected correctly. So there might be more. So you really need to take into account all the derived ones, and then you take those that only involve A and B. So there is a systematic approach that is very brute force. You could actually do it on paper if the set is small, but I'm warning you, it's brute force. So how can we try to derive all the possible functional dependencies ever that can possibly follow from that? Well, let's try to think of what are all the possible left-hand sides. So what are the possible left-hand sides? Let me ask differently. How many possible left-hand sides can I have? For the one on the right with ABC. How many possible left-hand sides can I have in functional dependencies for the ABC? Yes?
Well, 2 to the power of number of dependency.
Exactly. That's known as the power set, right? So you take ABC and list all possible subsets, right? Who knows the power set? That's called the power set. I'm not seeing any raised hands. Okay, yeah. So this is the power set. It's all possible subsets. So there's 0. You do it by cardinality, right? 3 of them have 1 element, 3 of them have 2 elements, and 1 of them have 1 element. You know Pascal's triangle? Who knows Pascal's triangle, right? Okay, so that's basically very related to that. Okay, so all subsets. And what do you do with that? Guess what? You compute the closure of all of them. So I did it for you. For example, you see that the closure of A, if you start with this one here, the closure of A is ABD, because A you can derive D and then you can derive B, so that gives you ABD, and I computed the closure for all of them. Okay, so that's very brute force, but that's something I warned you about. And then what do? You clean it up. So you basically compute the minimal basis. Of course, you get rid of everything you're not interested in. So D, we don't care about, we remove it. Then we compute the minimal basis, okay? So let's do it. Let's clean that up. Do you agree I can get rid of this one? Yeah, so let's get rid of that one. Anybody else? Let's do it together. What can I do? Anything trivial that I can throw away. So of course, there's not a unique path, right? Might be multiple paths. Yes?
Well, first AB don't give B, the second line gets away.
Yeah. That goes away, yes, I agree.
C give AB.
Yes, you can remove the C, absolutely.
This one, yeah, this one disappears. Below we have AC give B.
Yeah.
BC give A, and the last one disappears.
And disappears. Yeah, absolutely. This is pretty much it. So let's see. So here, I'm doing what probably similar to what you said. So we're removing A, that goes away, removing C, this goes away, A and C go away, B and C go away, and this goes away. Yes, exactly. And then we iterate. So now can we iterate on that? Is there anything else we can do here? Maybe yes, maybe no. Let's see. Yes, there is one more thing. Yeah. Exactly. C gives you A already, so the B is useless, right? This is what you're saying. So let me split it, right? We can also split it. And then there is C gives you A, so this is redundant. So, oh, this one is redundant too, right? C gives you B, so that one goes away first, and this one is redundant too, right? You see what we can achieve with cleanup, right? It's very, very minimalistic. So this is it. I think we are done. A, B, C gives B. Oh no, we can get rid of C gives B too, right? Transitivity. Yeah, just these two left, right? Who agrees that now we have what we want? We projected these functional dependencies for that table, and now we have A gives you B and C gives you A, right? So this is the projection. And you see why I give you my word of warning. A gives B didn't appear explicitly here. We derived it and then realized it applies. C gives you A, that's the same. We derived it. So this is why you cannot just take whatever has A, B, C, and be done with it. You really need to go through deriving them. Okay, so this is it. So what we say is that when we projected the table onto the attributes A, B, and C, we also projected the functional dependencies onto A, B, and C, right? Who is with me? All right, very good. That's going to be a useful milestone for later. Now, here's you will slowly see coming the reason why I have told you that. The idea is that now I'm back to my initial problem. I have a web shop and I have a bad design in my database and I have the gigantic table that tries to do everything. And I'm wondering, like, how can I fix it, right? And I already told you that the best practice is to have multiple smaller tables where every table does one thing. There's a table for the product, there's a table for the customers and so on, instead of a single big table. So the question we ask is, first, do we like this table or don't we like this table? And then if we don't like it, then what can we do about it, right? So once you have decided that you don't like it and you want to split it, so you basically need to decompose it, what is going to happen when you decompose the table is that you're going to select one side of it. So let's split it into two. The first split might have these attributes, for example, A and B, and the second split might have A, C, and D, right? Why? That I will tell you, right? Here I did it a bit at random, like this, picking this, but there is a way to select the projections that you want. But do you agree that basically we are projecting the table onto the first set of attributes, and then we are projecting, there's a duplicate, then we are projecting the table onto the other set of attributes, and that's it. And so basically decomposing a table means that we split it in this way, projecting. Note that the two projections have columns in common, right? If you completely split and it doesn't even overlap, then that's you're losing information, right? You still want to be able to join them back into this, right? So this is the idea. So you really see this idea of decomposing, and then you want to join it back. It has ideally to give you the same thing and equivalent data. Who is with me? Right? Okay. All right. But the thing is, we cannot just do it at random. We cannot just randomly pick attributes and projects and that's it. We really have to pay attention and be smart on the selection of the attributes that we take in order to project. So now that's just formally what I've just told you. You basically take a relational table. You have two sets of attributes, S and T. What you want is that their union gives you the whole support of R, right? You don't want to forget columns. You really want all columns. So the union of the two sets of attributes here, that would be AB and ACD. So the union of AB and ACD, that's ABCD. And S and T, I didn't put it explicitly, but they should normally overlap, right? It's if in the real world, they will typically overlap. If you can decompose the table in such a way that S and T do not even overlap, that really means that your initial table was a big mess, in other words. So R can be decomposed into the projection onto S and the projection onto T, and that's really a replacement. Like you throw R away and you only keep the decomposed version, right? But we need to do it wisely. And in order to do it wisely, we need a goal. We need a criterion that tells us that we like or we don't like a table. And hopefully we turn a table that we don't like into several tables that we like. But what does it mean to like or not like a table? Well, it means that it is or not in a normal form. A normal form is a constraint on the table, typically using functional dependencies. We'll show you. And they are organized in a stack. There is the first normal form, the second normal form, the third normal form, the fourth normal form, the fifth normal form, and the sixth normal form. And there might even be people who found others. Plus, between 3 and 4, there is a 3.5 normal form, right in the middle. But we usually, I mean, it's nicknamed the 3.5 normal form, but it's actually the Boyce code normal form, BCNF. It turns out that the BCNF, the Boyce code normal form, is the easiest one to learn. So this is the reason why I'm going to be showing this one to you, but you should be aware, I will quickly give you the others, some others. But BCNF is the easiest. That's the easiest to spot. And in practice, if you design your web shop and it's in BCNF, you're good. That's good practice. That's already good enough. All right, so Boyce code, normal form. You already know code, right? Data independence, Edgar code. That's the same. Person. Raymond Boyce is the other. Okay, so I will now tell you what the Boyce code normal form is. By the way, I think I already told you. You already know the first normal form, right? The first normal form, that's when the values are atomic, right? You don't have anything nested. So the first one you already have, and that's the 3.5. Okay. So here's this table, ABCD. I put some data in there. That doesn't mean anything, so let's consider it just math. You notice that it has functional dependencies. Do you agree that A gives me B? You see if here, the same value gives you the same value, right? So there is a functional dependency from A to B, and there is also a functional dependency from C to D, right? You see it's the same value, and that's also the same value, right? For this table, right? Okay, so I have A gives me B and B gives me C. Could you tell me what the transitive closure of AC is? Maybe you can directly say, yeah, ABCD, exactly, right? For this, I need to use all kinds of actions and rules in order to derive this. But I think you use the augmentation rule, so you can deduce that AC gives you BC and AC gives you AD, and then you can combine them into AC gives ABCD with the combined, so augmentation plus combining rule gives you that, right? But of course, it's so intuitive that you probably didn't even have in mind that you were using the augmentation and the combining rule, right? It was done intuitively, okay? Which is fine too. Okay. Now, what is special about this functional dependency, especially about its right-hand side? In other words, what can you say about AC? On Zoom, maybe? Yes? Yeah, and that means that AC is a? It could be, yeah. And before going to the primary key, before that? Yes, it is a functional dependency that leads to the entire table. That's the definition of a super key. It is also a candidate key because you cannot remove A or C. And because of that, you can decide that AC is the primary key, right? So this is the reasoning. For the purpose of defining the Boyce code normal form, I'm going to stop at the fact that AC is a super key, right? Who agrees AC is a super key? All right, so AC is a super key. I love that. I love seeing functional dependencies that determine everything. I love seeing functional dependencies when what is on the left is a super key, right? And that's the Boyce code thinking. We love it when the left-hand sides are super keys. But I don't like this one. I don't like these ones because A is not a super key. Do you agree that A is not a super key? Right? The transitive closure, the closure of A would just be AB, right? That's it. And the closure of C would just be CD. So we have functional dependencies where the left-hand side is not a super key. We consider these functional dependencies to be undesirable. The one at the bottom, AC gives you ABCD, this one we like, right? Because it's a super key. Okay. So this table here basically has functional dependencies that don't have a super key on the left, and they're also not trivial, right? If they were trivial, we wouldn't care, but they're also not trivial. So in fact, this one is not in the Boyce code normal form. So this one, we have to do something about it. What about this one? Do we like this table, yes or no? So we look at the functional dependencies. Well, for example, we have AC gives you D, right? But this one we like because AC determines everything. So AC is a super key. So that functional dependency is fine. There's also AD gives you C, but AD, do you agree it's a super key, right? The closure of AD is ACD. and CD gives you A, the closure of CD is ACD2, right? So do you agree that AC, AD, and CD are all super keys? Who agrees with that? Okay. So here we don't see any problem. You can try to see if you find others, but I don't think, because I carefully picked the data in there, you will not find any other functional dependencies, except the trivial ones, right? There's still the trivial ones like A gives you A and so on, but I really mean the non-trivial ones. So here, that's really perfect because all the non-trivial functional dependencies have a super key on the left. This we like. This is the Boyce code normal form. So this table is in the Boyce code normal form. So we don't need to fix it. It's already good. So now I give you the formal definition, but by now you understood it. We say that a relational table or relation or a table is in Boyce code normal form if the only non-trivial functional dependencies have a super key on the left. So we forbid non-trivial functional dependencies where the left is not a super key. For whom is that clear? Okay. And again, for the trivial part, why do I say non-trivial? Because if you look at the non-trivial dependencies, you could have A gives you A, B gives you B, C gives you C, even though A, B, or C are not super keys, right? But again, they are trivial. They always exist, and we don't care about them, right? So like AC gives you A, and so on. So these are the ones considered trivial. This is basically those that use the reflexivity rule that makes functional dependencies pop up out of nowhere. Okay. Now I have a mini theorem for you that's kind of cool. Is that if I give you a table with 2 columns, you don't even need to think it's in Boyce code normal form, guaranteed. You don't even need to check. It's always the case. But it's interesting to actually look at it and see why that is the case, that it's always in Boyce code normal form. So these are the 4 possibilities, in fact, of functional dependencies when you have 2 columns. The first possibility is when there is a super key that's all the 2 columns, A and B. You agree that A is not a super key and B is not a super key in the one on the top left, right? A is not enough and B is not enough, right? So the super key would be AB, and that's also a candidate key. Do you agree? Now you look at the top right. Here, I have the functional dependencies that A functionally determines B, right? So A is a super key, and of course, AB is also still a super key, but A is a super key. What is the candidate key here? That's A, right? AB is not minimal. That's not a candidate key, but A is a candidate key. Here, I have that B functionally determines A, so B is a super key, right? And here, everything is a super key, right? By the way, when you have a super key with only one attribute, how can you say it's a super key? How can you tell a super key with just one attribute? There's a very easy way to see it. Yes? Exactly. All values are unique. If you look at a single attribute, if all values are unique, that's a super key, period, for that table. Okay. Do you agree these are the 4 cases? These are the 4 possibilities that I can have for 2 columns, right? Okay. But then, if you look carefully, they're all in the Boyce code normal form. Because the one on the top left, the only super key is AB, and you don't have any functional dependency with just A or B. That doesn't exist. The one on the top right, there is a functional dependency. A gives you B, but A is a super key, so that's fine. And B cannot give you any functional dependency. It doesn't determine anything except trivially. In the bottom left, B gives you A, but that's fine because B is a super key. And A is not enough to identify B, so that's fine. It would only identify itself. And then the last one, you have A gives you B and B gives you A, but both A and B are super keys, so this is fine too, right? So you see that in each one of the possible cases, we only have non-trivial functional dependencies so that the left is a super key, right? So if you have 2 columns, that's it. You never have to decompose a table with 2 columns. I also don't know how you could decompose it further, except that 1 column, but again, that wouldn't be very useful. Okay. So now we can formulate what we want to achieve. We have a table that is not in BCNF. It's not in Boyce code normal form. And we would like to decompose it, meaning to project it onto two smaller tables, such that these tables are in Boyce code normal form. That's what we would like to do. It might be that it's more than two tables. Could be three, could be four. You just decompose multiple times. But what you want is that all of the tables at the end must be in Boyce code normal form. Now, if I stick to that and formulate it simply, I would like you to see that the problem is too easy, because I could just project it to tables with two columns each and be done with it, right? Because two columns are in Boyce code normal form. So what prevents me from doing that, right? I can just do it and that's it. We're done, right? But of course, that's not it, right? Because there's still a problem with that. That's actually not the way you have to do it. And the problem is this. If I just take subset of two attributes and project onto it, the problem that I will have if I just do it completely randomly is that if I take now these tables and I join them back into this one, you can compute the join of this and this and this, the natural one, using A as the joining key. Try to do it on paper. To do the join of these three tables, what you will notice is that you do not get this. You actually get something bigger. You will get more records, phantom records that appeared out of that, but they didn't exist in here. And this, in fact, is a loss of information when that happens. So it means that this decomposition, it might give you tables that are in Boyce code normal form, but the problem is that the data is different because you cannot reconstruct the original table. For whom is that clear? Right? So it's sad, right? Because I would have loved for it to be that simple, right? To just solve it. But no, that's not how it works. So in fact, we need some methodology. We need a way to proceed with caution. But now if you think logically, why do we want to decompose that table? We want to decompose that table because it breaks the Boyce code normal form. What does it mean that it breaks the Boyce code normal form? It means that I have a functional dependency such that the left is not a super key, exactly. So that's how we start the reasoning. We just take one of these functional dependencies such that the left is not a super key, right? The next thing that I do is take the closure. I think transitive closure, it's the same thing, the closure of that set of attributes. So I'm taking the one on the left. So in that case, it's A, but that could also be multiple attributes. And I'm taking the whole closure. So imagine here, I just modified the table to show you an example. So here, for example, I might have A functionally determines D, but you would have to also throw in C, right? Because I just modified the data. Just to give you an example here, I modified that value in here. And when I do, then A functionally determines C. So you always need to take the entire closure, not just the right-hand side, but the entire closure. You know how to compute a closure, right? That I told you, and 100% of you gave me the right answer. So you basically take that functional dependency that breaks BCNF, because that's not a super key. You compute the closure. Is it possible that the closure is the whole table? No, because it's not a super key, right? So since you know that this is not a super key and you compute the closure, you know it's not going to be the whole table, right? So that's good. So what you do is then, once you have taken that functional dependency and computed the entire closure, so all attributes that depend on it, you use all of these as your first projection, right? So you take the left-hand side, union the right-hand side, the entire transitive closure, that gives you your first table. Can you guess what the second table is going to be? The second projection? What attributes will it have? Yes? A with the rest, exactly. So you keep A, that you need on both tables because you need to be able to join them back. So you really need to realize that the left-hand side is your pivot. That's the one that joins the two. So we take, that's MA, and now we throw in all of the other attributes that were not in the transitive closure of A. Okay? For whom does that make sense? Right? So this is how we do it. We do not project randomly. We project in such a way that one of the two sides is built from a functional dependency that breaks the condition, right? Do not forget to take the entire transitive closure. That's a common mistake that can be made. You really need to make sure you have the entire closure of the attributes on the left. And then the rest on the right. Okay. And then what happens is that when you do it in this way and you project back, but I will show that to you formally and with an algorithm, then you can actually get back the original table. Okay. Well, here we were lucky because now both are in BCNF. That's not always the case. It might be that they are not both of them in BCNF, then you just reiterate with even more decomposition, right? But here we were lucky, they are both, so the one on the left, because it has two columns, so that we can also already say for certain. And the one on the right, if you look closely, you will notice that you don't have any functional dependency so that it would be not be a super key, right? You can look, I didn't find any. I think you will not find any either, right? So BCNF. And again, I insist that the whole reason we've been doing it in this way is that when we take these two tables, now we forget the first one, if we take this decomposition and we join them back, natural join based on A being the overlap, so this join, we retrieve the original table. Okay, exactly it. So this is basically now an interesting mathematical problem. Can we prove that in some way, right? Because it's a fair question to ask, right? A priori, there is no reason why it should be exactly the same one. So we ask the question, when we have decomposed in that way, do we retrieve the exact same table? Do you know how mathematicians prove the equality of two sets? These are two sets, right? A table is a set of records. So we want to show that the set of records corresponding to the table on the left is the same as the set of records of the table on the right. How do you prove that two sets are equal? In two steps. Is there any mathematician in the? Yeah, exactly, the inclusion on both sides. So you prove that the left is included in the right, and you prove that the right is included in the left. And if both of them hold, then you have an equality. That's exactly what we do here. We just prove inclusions. So one side of the inclusion is to ask, is the original relation a subset of the join, right? In other words, if I take a tuple, any tuple in the original relation on the top, is that tuple also in the join? In the join. In fact, this one is trivial. That is the easy part of the proof. It's just because of the way you project, right? If you take, let's take this tuple. Let's imagine we have a tuple ABCD in the original table. Do you agree that that tuple is going to be projected on the two sides? On the left, you're going to have this, A and D, right? So this is what you have on the left. And this is what you have on the right. Do you agree that it will be in the join because you have that on the left that's going to be matched with that on the right? It's the same value of A, and you retrieve ABCD. So we've just proven that it was in the original relation, and it is also in the join, right? So what is for sure is that the join of the decomposition is going to be a superset of the original table. The worst that can happen is you get more tuples, too many of them, but you will not get less of them. You cannot lose any tuple. For whom does that make sense? Right. So that was one side, one half of the proof, so in one direction. And now we need to do the other side of the proof. We need to show that we also have an inclusion the other way around. So it means if I take a tuple in the join, is it yes or no in the original table? And this one is trickier. It's trickier because it's not always true if you do the decomposition randomly. But it turns out that a smart person, Chase, came up with an algorithm in order to determine that. And that's also something quite mechanical that you can do it with a pen and paper. And the way that this is done is, okay, let's reason like a mathematician. I want to show that the join is a superset of the original table. In order to show that, let T be a tuple of the join, and I want to show that T is also in the original table. So let's take a tuple T in the join. If it is in the join, then it must be in the tables that you joined on, right? So if you have joined two tables and you get A, B, C, D, then the tables you've joined must have a tuple on the left that has AD, and the other table must have a table with ABC, right? If that were not the case, you would not have had ABCD in the join, right? For whom does that make sense? All right. So it means that now I have two tuples, AD and ABC, that is in the original table. By the way, ABCD that I put in there is part of the Chase algorithm. Typically, you use letters. You can use any symbol you want, but this is basically variables. You give it the name A, the name B, the name C, the name D, right? And you want to prove that it's on the other hand. So now, the projection must be in the projected tables. But do you remember that these two tables, AB and ABC, how did we get them? We got them as projections from the original table. So it means that because AD belongs to the table on the left, there must have been some tuple in the original table from which it came from. So it means that there must have been some tuple that we can call T1 in the original table that had here A and here D and here whatever, right? Because it was projected, you agree, if you project that, you get this. So if you had this in the projection, you must have had a tuple that looks like this. Who agrees? And the same for the other. If we have a tuple ABC in the table on the right, there must have been somewhere it came from, and that must have been some tuple T2, ABC, and here whatever, from which it was projected. Remember what I want to show? I want to show that there is a tuple in the original table with ABCD, right? I'm not quite there yet, because now I have two tuples, one with AD, one ABC, but I don't know if they're the same or not, right? So now I have not proven yet that ABCD belongs to the original table. But I have proven that there is a tuple T1 in the original table with AD and a tuple T2 with ABC. And now, in order to show that there is a tuple ABCD in the original table that would conclude our proof, if we can do it, we are going to use the functional dependencies for that. So remember that I use the expression whatever to say what is in here and in here, in here. I just say whatever. Mathematicians don't say whatever, they just give them names, right? So let's say B1, C1, D2. That's the names we are going to give to them, which can be anything, right? B1, C1, D2. Now, you remember we have functional dependencies, right? Do you remember what functional dependency we had? Yes? Anybody? Yes? A gives D. That's how we picked the table on the left, right? From A gives D. So we picked A and D. What can you infer from that functional dependency? You can infer something here. A gives D, so yes? Yes, absolutely. So A and D would also hold here in that projection. This is absolutely true. And can you tell me something about the values here that are in that table? You see A, B1, C1, D, and A, B, C, D2. Can you infer some equality between some values based on the functional dependency A gives you D? D2 equals D, exactly. Do you see it? We know that D is a function of A. And here, we know that it's the same A, right? Because that came from the join and the projection and so on. So it's the same A. And because of the functional dependency, if it's the same value in here, then it must also be the same value in there. Who agrees? Right? It's the functional dependency. So D and D2 are the same one. So it means I can just put D in here. It's not anything, it's going to be D for sure. So I do it, right? Because of this. So I can just put D in here. Bingo. You see, it's like playing the bingo, right? Now you can say, bingo, yes, A, B, C, D. You have your full row, right? So this is how it works. That's the Chase algorithm. Now we have succeeded. We have just proven that A, B, C, D, which came from the join, is for sure in the original table. It means that the join is a subset of the original table. And now we have an equality between the two. So it means that the decomposition was successful, and it is what we call lossless. because it's exactly the same tuples in the join and in the original table. Right. So that's it. That's the bingo. Yeah, we have succeeded. It turns out that if you carefully do the decomposition, taking a functional dependency that breaks BCNF, taking the whole closure, and then you project in the way I've shown you, that will always succeed. It will always work with exactly the same pattern. But if you do not do the decomposition in this way, and you just pick a random decomposition, and you apply the Chase algorithm, you will realize that most of the time you'll be stuck. You will not be able to actually get the bingo. Okay, that's basically how it works. So basically what we have achieved is that we can decompose a relational table into relational tables such that they are in BCNF. It can be more than two, right? If it's still not in BCNF, I just recursively iterate and iterate and iterate, but at some point they will all be in BCNF. And it is lossless, right? It's a lossless join because with the Chase algorithm, I have demonstrated that the join gives you back the original table. So it means that concretely for your web shop, you can just use this decomposition instead of the original table that was too big. For whom does that make sense? Right. There is one thing I'm just wondering, do I still say? No, I'm not going to say it today because I want to finish on a positive note. So we succeeded. We have these two things, and next week I'll tell you there's one thing we don't have, but anyway, let's focus on these things. We decompose the table, it's all in BCNF, and we are not losing any data because it's lossless. The two sets are equal. We are almost there in database design theory. It's almost arriving to the last slides. So there's not much left. So this is your usual remote control to tell me if I'm too fast or too slow, or you can control the speed at which I'm going. That might be highly dependent on your background. So I imagine that those with more mathematical background might follow easier. Those with less of a mathematical background, maybe less, but I'm trying to really make sure that everybody understands and nobody's left behind. That actually looks, oh, and somebody understood everything. Now you can explain to everybody else if they ask questions. Very, very good. Okay. And I have a secret for those between 50 and 79. The secret is to just train yourself mechanically, like compute the closure of a set of attributes, compute minimal basis, do a decomposition, like take tables that break BCNF and do the decomposition, use the Chase algorithm and so on. The best way here, I know it's with pen and paper rather than with a computer, but with pen and paper, this is the way to learn these things. Just iterate and iterate. And when you've done it many times, at some point you will get the intuition. And of course, the TAs have prepared many exercises that will train you on concrete examples doing that. All right. So this looks good. So thank you very much for attending today's lecture. Enjoy the exercise sessions. You can ask questions on the forum, on the Moodle. You can send emails to us if there's anything. You should read the book, the chapters that I'm giving to you. See you next week at 10 a.m. Thank you.